Okay, so let's start with the next lecture that is about image histograms. So an image histogram is a totally, so a count of how many pixels have a particular value. So let's see some examples. I think it is easier. So let's say that we have this image and we count how many pixels. So let's start with monochrome images. Gonzalo, ¿a qué venías pensando un sitio?
Pues sí, la verdad.
Mira,
A ver, dice, doctor, últimamente veo elefantes azules. Dice, ¿ya ha visto usted un psiquiatra? Dice, no señor, son elefantes azules.
Bueno, so we have a gray image like this one, and then we count how many times we have seen a pixel with value 0, and you count how many times you have seen that, and you put it there. How many times you have seen a pixel with value 1, with value 2, with value 3, and you annotate here how many times you have seen those pixels. And this image is pretty dark, and that is why you have a peak at very low intensities. And we have very few bright pixels, mainly here, and then the bright pixels count is relatively low, relatively or rather low. Okay, so this is one example. Let's see another one. So now we have a much brighter image, and this much brighter image now has many more bright pixels, and also we have some darker areas. And actually we have two kinds of dark areas. So one is the trees here, the other one is the ground. So those are the two bumps that we see in the histogram. And there is something else that already appeared, this concept yesterday, that is that an image may not use the whole dynamic range that it has. So it is allowed to take pixels between 0 and 255, but for instance, this image, the region from 0 to 75 doesn't use it, and the region from 175 to 255 doesn't use it either. So that means that we could increase the contrast of this image simply by expanding this histogram. So if you map this minimum to 0 and you map the maximum to 255, then you would be better utilize the dynamic range that you have in the image. So the number of possible values that you're allowed to take. Okay, so this is another example, much brighter image now, and a better utilization, better use of the intensity range, and now you can recognize the different regions. So, for instance, this is the snow, and there is another feature here that we didn't see before, that is saturation. So you see that at 255, that is a large number of pixels. So large number of pixels means you have your sensor is collecting photons, and it is counting how many. But at some point, it saturates, it just stops counting. So you have reached the maximum voltage that the sensor is capable of having. So once you saturate, more photons arrive, but you are not able to count anymore. So this saturation is a characteristic, and it may saturate on the bright side. You may also saturate on the dark side. So there is a minimum amount of photons that you are able to receive. This minimum typically is related to noise, so some kind of electronic noise that makes you to detect even if no photon is arriving. Here is another example, but now with a color image. So if you have a color image, you have 3 histograms, one for each channel. And here we have the histogram for red, the histogram for blue, green, And we already recognize all these features we have been talking before. So we have saturation here. We have, for instance, some dynamic range or some part of the range of intensities that is not used. Also, we see, for instance, the blue sky. So, for instance, this peak is the blue sky, you think, or not? This is the blue histogram. So this peak corresponds to this part of the sky. What would you say? Why? Exactly. It is dark blue, so it cannot be this one. It has to be this one. There is a big part of the image that doesn't use blue because it is red, actually. It is mostly red. So it doesn't use much blue light, and it is all this part of the mountains. So this part corresponds to the mountains. And then red, most of the image is red, and we can see that the histogram of red is pretty flat, meaning that we need all kinds of red. And yeah, this is the sky, this part here, the blue in the blue histogram. And then green again. We don't see much green, and that is why the peak of the green histogram is in the dark area. Okay, so another example. So here, most of the image is green, and we see that the green histogram, especially at high values, is taller than the rest of the histograms. And we don't have much blue, so that is why the blue histogram has a peak here in the very dark area. We don't have much red either, so that is why also. And this is also a bit surprising. So most of the image is green, but you have here the peak of the green is in the dark area. So meaning that even if many things are green, there are many other, like all the stones and all these dark areas that they don't use so much green. So another example, so yeah, saturation again. We don't need much blue. So what is the frog here in the histogram? This peak? No. This peak is just not a few pixels, but there's some small regions here that are very bright in blue. It is mostly probably this peak here and this peak. So that is a frog. And then the rest of the, for instance, the stones here, they look kind of reddish. So that is why you have the histogram of red a little bit shifted to the right. Another example. So yeah, now once you start understanding how this works, you can play a bit with all these possibilities. Okay, so let's try to formalize that a bit. So a histogram is a function that given an image, for instance, the image G, it counts. This is this symbol. So the hash symbol is the count of this set. Sets are typically denoted with curly brackets. So it is the count of elements in this set, and this set is number of pixels such that the image G takes the value G, the small g. And the range is from an image. So what is the argument of the argument of the histogram? It is a gray value, so it has to go from 0 to 255. And what is the domain? Domain is, it is the opposite. So this is the domain, this is the range. So the domain is from 0 to 255, right? The range is what values it is allowed to take. So at most, if the image has R columns and R rows and C columns, the maximum value it can take is R times C. And this brings me to introduce a concept that I think it is very much into all this nature of image processing. And that is you can see what I draw here, right, from home. Can you see?
No.
No veis nada. Si dibujo eso no lo veis. No lo veis.
Yeah, siguiente.
Okay. So I said that the first day, this is kind of continuation of signal processing. Okay, so let's think a bit of what signal processing is and how this goes into image processing. Okay, so a signal processing, so you are familiar with this x of t. X of t, this is the t-axis, this is x of t, and then you have some signal here. And so x of t is a function that takes an argument from the real set, and it produces another value in the real set. So the first R, this one here refers to time. The second one, this one refers to the domain of x of t. So this is called the domain. This is called the domain, this is called the range. Okay, so you have now, for instance, let's say x of n. So you have x of n. What is the domain of x of n? Those are integers, n. So I got too close. So it is the set of integers. And what is the range? R. And then we have, for instance, Fourier transform. So let's say that we make a Fourier transform of, so this is the Fourier transform of x of n. And this is a function that goes from where to where. So what is the domain of that function? No, it's frequency. So frequency, it goes real number. So this is a real number, and it goes to n. Set. No. They're not integers. They're complex numbers. The Fourier transform of a discrete signal is the Fourier transform is always complex, right? And why this is important? Because an image is just another signal. So an image, when we say RC, what is the domain? Z squared. So Z squared. Squared means that, so this one means that we have two arguments. And what is the range? 0 to 55.
Okay. Prove the number of rows and the number of columns. Depending on RC.
No, but what is the range? So what are the values that I is allowed to take?
0 to 55.
Yeah, 0 to 55. So 0 to 55. Actually, if you want to be very precise in the notation, so that is a continuous range. So it can take any possible value between 0 and 55, which is not true. For instance, if we want to be very precise, you can do it in two ways. So now you can say intersection with the set numbers, and then you have only the integers between 0 and 255, or you can put it also like this. So 0, 1, 255. And now you are using the curly brackets to say that it is a set, and these are the elements of that set.
And can we see that those numbers belong to set with an int?
That those numbers belong to some set? No. You can say, for instance, you can write, the right notation would be this one. I of RC belongs to 0, 1, 2, 5. This would be the right notation.
Okay.
Yeah, but this is for a gray image. What if we have a color image? Okay, so I have 3 of those. So how do I say 3 of those? The cube. If I want to use this notation, the cube. And now we have introduced another function that is the histogram. So the histogram of an image, and we have defined it only for gray images. So actually, let me move that one. So for image G, it is something that takes a gray value, and returns a count. So gray values can be 0, 1, 255, and then it goes to 0 RC. So at the end, all image processing, all signal processing is handling functions. So that is why all the Fourier transforms, for instance, and all the other transforms, you have only seen the Fourier transform, but there are many other kinds of transforms, like the wavelet transform or whole transform. There are many kinds of transforms. So all these transforms, they come from the world of functional analysis in mathematics. Okay, so any questions so far? No? Okay, so let's go back to this. Okay, so this is what we have here. So the histogram of a gray image is something that takes a gray value and returns a number between C1 and RC. And this is the same. There is nothing new here. Okay, so let's see. There is this G plus 1 here. It is simply kind of mixture between MATLAB and mathematics. So in MATLAB, the first element of an array is element 1. But in mathematics and the functions we are defining, we are saying that our images go from 0 to 255. So I cannot access the histogram at 0. So the histogram of value 0. So somehow in the slides it is intermixed these ideas between mathematics. So having histogram of G, but then also the where to store it in MATLAB. So that is why he's having 1. But forget about the 1. The important part is the dependence of G on G. Okay, so I can, for instance, let's say that I have this gray image and I compute the histogram. And the histogram also can be understood as a probability density function. So it is the probability that if I take a pixel at random from the image, I have that value. And to be a probability density function, what I need is, let me go back. So let's call it G, sorry, let's call it small g. So the small g, if it is a probability density function, it has to fulfill one property. Which one it is? All probability density functions have to fulfill some properties. They have to be larger than 0 because probability is. So this is a discrete or a continuous probability density function. How do you know that?
Depending on the image.
It is discrete. Why?
It doesn't take anything.
Yeah. Because the argument, this argument is discrete. This is discrete. So it is a density function that is defined for discrete values. Okay, so the properties to be a probability density function is that it has to be positive. So if it is a discrete probability density function, this is not true for continuous, but if it is discrete, then it also has to fulfill that it is smaller than 1. It is smaller than 1, and that is another constraint. Yeah. The sum over all these of the function has to be 1. So how can we define, once we have this count, how can we define a true probability density function? So what we can do is we can define it in this way, and you tell me if it is clear. So it will be h of g divided by the sum of all. So that function fulfills the three properties. So it has to be larger than 0 because this is a count, and a count has to be larger than or equal than 0. And the sum is 1 because we are dividing by the total sum, and this is just the. So we would have, if we add this thing, at the end we have 1 divided, or something divided by itself, so that is 1. And yeah, and it is smaller always than 1 because this is the maximum value you can have. Okay, so actually this, what is this sum? This sum is equal to no. This is the total number of pixels. Okay, so I could also write it in this way: 1 over RC HG. Okay, good. So that is to say that if I have these histograms together, so the scale has not been drawn there, but if I scale it in such a way that the sum is 1, then this is the probability density function of the random variable. That is, you take a pixel at random, what is the probability that it takes a value 100, or what is the probability that it takes the value 50? And then you can compute means, standard deviations, medians, you can compute whatever. Because once you have a probability density function, it's very annoying having to go from one to the other. So once you have a probability density function, I can compute the, what is the, what is the mean of G? So it is the expectation of G, and this is the sum of all G's of G times the probability density function of taking that value. And I can compute that. I know everything there, so I can compute the mean of the G values. I can also compute what is the standard deviation of G. So the standard deviation of G, let's put it squared, so this is a variance. So it is the expectation of G minus the mean of G squared, and this is the sum of all G's, G minus G, and then okay. So you can compute all kind of statistical descriptors of your image. Okay, so let's go back. This is what has been done here. Okay. Then let's see more examples. So let's say that we have this image, and then we can do the following. So I can decompose this image into several layers. And these layers will have 0. They will be 0 if G is equal to 0, and 1 if it is different from 0. Okay, so I'm marking all pixels that have a value G equals 0. So first of all, this image has been quantized with 16 levels, that is 4 bits. So the gray values go from 0 to 15. And then I'm not only counting how many pixels in this image have value 0, but I'm also representing them in an image. So all these dark points here, they have value 0. And those are 29, 32 pixels. And then how many have G equal 1? And then it is those ones here, and 24, 54. And how many have G equal 2, and so on. And then we can try to see if these layers are consistent with what we know. For instance, these pixels here, they are the brightest ones, and they appear in G equal 15. And then these ones here, they're also pretty bright. They appear in G equal 12, G equal 11, that is above the average. So the average, the middle point is 8. So this is a little bit brighter than the middle point, and that is why they appear at G equal 11, G equal 12. And the same happens with the legs of the insect. So they are pretty dark, and they appear mostly in G equal 0, G equal 1. You see? Okay, good. So it is not only that we can count, but also we can know where those values are taking place. And then the histogram is simply a count of how many pixels are in each one of these layers. So you can see the histogram as the count of each one of the active pixels in those layers. And again, this is one of the practice you can do. So in this document of possible practices, so we have already seen a few. So for instance, you can decompose an image into different, so let's annotate them together, because otherwise I would forget very easily. So let's go to, I think it is here. And feel free to add your own practices. So those are the ones that I think of, but those are not the only ones. So, 3. is one price and it's another one is show the stack layers and then the histogram, which region is has values, so numbers. Yeah, I think those are most of them, right? A computation of the histogram. And following this. Okay, so those are a few. Okay, you are many in class, so be creative about what applications you can find. Okay, so we are here. Good. So for color images, it is the same, but now instead of having just one histogram per image, we have 3 histograms per image, one for each one of the channels. So this is what is said here. Yeah, so here it is. So the histograms of each one of the channels. And we will see later something that is called the luminance. So the luminance is how to transform a color image into a gray color image. So we can transform this one into something like this. Okay, so what is one sensible way of doing that? Okay, so there are many possibilities. One of them that is the most obvious one, it is to compute something that is called the value image. So the value is simply the average of the 3 channels at that point. Then, yeah, here what we have is how to do that in MATLAB. The other one is this luminance. So if you look at this formula here, so this formula here is red channel times 1/3, green channel times 1/3, blue channel times 1/3. And this has this structure. So let's move it up. So what we are doing is something like this. So the luminance, or whatever gray image, I will call it G for gray. So it is a weight in the red channel times the red channel plus a weight in the green channel times the green channel plus a weight in the blue channel